Hi, I'm Tom Newman. I'm the project scientist on the ICESat-2 mission. NASA's Ice, Cloud, and Land Elevation Satellite 2, or ICESat-2 as we call it, recently celebrated its second year on orbit after launching from Vandenberg Air Force Base on September 15th, 2018.
Hi, I'm Caitlin Harbeck, and I'm the Data Product Manager for NASA's Ice, Cloud, and Land Elevation Satellite 2, or ICESat-2 for short. For this Photon Phriday example, we actually took data from the same orbit collected on two different dates to capture the clearest, least cloudy data examples.
ICESat-2's main objective is to measure the elevation of the Earth, and as the name suggests, it's optimized to measure changes in icy areas. The way it does that is to transmit a very small pulse of laser light, green laser light in our case, and precisely time how long that light takes to go from the spacecraft to the ground and back up again, by combining that round-trip travel time information with information on where the satellite is in orbit and what direction it's pointing. Through ground processing, we can determine what the elevation of the Earth is beneath the satellite. This is an example of the data we collect, known as ATLO3, the Global Geolocated Photon Product.
Hi, I'm Nathan Kurtz, the Deputy Project Scientist for ICESat-2.
Now we're into the Arctic. This is where I'm familiar with, especially Arctic sea ice. You can see it kind of looks like an ocean return, but there's not quite as much structure. The sea ice surface isn't as rough as, say, a ocean that has a lot of swell and waves, so that return isn't as thick. The little structure that you do see is really from the ridges and things that are in the ice, so the ice kind of gets crushed together in places, and so that causes those returns. So now we're over Greenland, and you can see Greenland's really high. You can see this really like dome-like structure, and that's interesting because it's how the ice sheet forms. Like, it gets really high near the center, and gravity is just pushing this down all the time, and so the ice is slowly flowing out to the ocean. So you get this dome-like structure, but obviously here we're seeing more topography, things like mountains and stuff that the ice flows around.
For each of the photons detected by ICESat-2 on orbit, in ground processing we determine the latitude, the longitude, and the elevation of each one of those photons.
These large collections of photons make up what we call the photon cloud. The photon clouds you're seeing on the screen now are examples of this ATLO3 data product collected along reference ground track number 1352. These photon heights have been corrected for various geophysical phenomena, such as atmospheric effects and tides.
The photons colored in green indicate photons that ground processing has identified as most likely reflecting off the surface of the Earth. Over the oceans, we can see that the surface is very flat, much like we would expect. If we zoomed in on some of these areas, we can see that the Atlas instrument aboard ICESat-2 is actually able to detect individual waves and ocean swells that are just slightly higher or slightly lower than the surrounding area. We also notice that the width of the photon cloud changes around the orbit. Over oceans where the surface is relatively flat, that photon window is fairly narrow because we have a very good idea ahead of time of where the ocean surface should be. As we transition onto land, the width of that photon cloud gets much larger because there's a lot of roughness and topography over the terrestrial parts of Earth or over the ice sheets. And so ICESat-2 sends down a much wider band of photons over these areas in order to capture that surface. We notice that in some areas there's relatively few photons, and at other points around the orbit the plot is almost solid with photons. And that's mainly due to the effects of the sun. Atlas uses green laser light, and it turns out that the sun also emits a lot of light in the green part of the spectrum. So when ICESat-2 is collecting data over sunlit surfaces, we see a lot of background photons in addition to the photons reflected off the Earth. In contrast, over dark surfaces at night, we see relatively few background photons, and we get a really clear surface return.
That sharp diagonal feature in the photon return is from something called the transmitter echo path, or TEP. It comes from routing of some of the transmit laser power through to the detectors directly. Because we have two different TEP paths to know exactly how long the path delay should take, we're able to use deviations in the TEP to calibrate the instrument to account for things like thermal variations.
At times, Atlas's onboard signal finding that is used as a first filter to approximate where the ground surface is located is unable to find the surface returns owing to the reflection of sunlight from clouds. In those cases, the telemetry band may or may not include the surface. The telemetry band can change every 200 shots, or roughly 140 meters along the satellite's track, which takes roughly 5/100ths of a second to complete. The discontinuous bands of telemetered data and blocky features that you may be seeing on your screen are due to Atlas detecting clouds and not necessarily the ground surface.
As we transition across the center of Antarctica, one area of interest, for me anyway, is a place called Hercules Dome. The National Science Foundation has funded a number of deep ice coring efforts in Antarctica over the past several decades that are all aimed to drill down through the ice sheet and collect ice from far back in time. The ice closest to the surface of the ice sheet is the youngest, having fallen as snow relatively recently. And as we drill deeper and deeper into the ice sheet, we collect ice that fell as snow many thousands of years ago. Hercules Dome is an interesting place to drill an ice core because it sits near the mountains, right at the edge between the East Antarctic ice sheet and the West Antarctic ice sheet. Models and observations suggest that the West Antarctic ice sheet is a much more dynamic ice sheet than the much larger and most likely much older East Antarctic ice sheet. And by drilling right at Hercules Dome, scientists hope to be able to understand how those two ice sheets have changed through time relative to each other.
ICESat-2 has a 91-day repeat orbit cycle and a 92-degree inclination. ATLO3 is one of the primary sources for all of the photon information required by higher-level data products, such as land ice height and sea ice freeboard.
As ICESat-2 transitions from taking data over land to collecting data over ocean, at times you'll notice we have a return off the ocean surface, but we also have a fainter second return, and that's due to photons penetrating down through the water column and reflecting off the seabed before returning to ICESat-2. In that way, we're able to use ICESat-2 data to determine shallow water bathymetry around the planet. Determining bathymetry is not one of ICESat-2's primary objectives, but it is something the scientific community is very interested in. In very clear water, photons from ICESat-2 can penetrate down through the water column, reflect off the ocean floor, and travel back up to the spacecraft. By looking at our data so far, we note that ICESat-2 can measure up to 30 meters of water depth, or nearly 100 feet. As the turbidity of water increases, or there's more waves at the surface, we can only see very shallow water depths, perhaps just a few meters. Measuring bathymetry with ICESat-2 is one of the many things that we've discovered in our data over just the first 2 years of the mission. Scientists are just publishing initial papers, and we expect many more discoveries over the following years.